complex numbers, because we use cis theta or mod arg form, which involves cosine and sine, there actually is a really nice crossover with using complex numbers to prove some of the results we've already seen, plus some other results as well. So, for example, cos 2 theta and sine 2 theta. Obviously, we already have a result for those. But here's how we can prove those using Demand's theorem. Because I could say, well, hang on, by Demand's theorem, cos theta plus I sine theta squared is the same as cos 2 theta plus I sine 2 theta. Now, if I expand the right-hand side out, then the real part must equal the real part, and the imaginary part must equal the imaginary part. So, cos 2 theta is cos squared minus sine squared, which of course we saw before. And sine 2 theta, 2 sine theta cos theta, which is of course a much quicker proof than the way we did it before. Let's try and prove results for 3 theta using the same idea. Well, same idea. If I used the Moivres, I could say, well, cos 3 theta plus I sine 3 theta is the same as cos plus I sine all cubed. Expand out my cubic, so cos cubed 3i sine theta cos squared, etc., etc., etc. Equate the real and the imaginary. There's an expression for sine 3 theta. It's in terms of cos and sine, but then of course we could substitute in 1 minus sine squared for cos squared and reduce it all the way down. And cos, we could do a similar thing. The question also said tan 3 theta. Well, now I know sine 3 theta and cos 3 theta. Tan 3 theta, sine on cos. Now, that's in terms of sine and cos. If I want to make it in terms of tan, then we need the cos on the bottom. So what I do is I'll divide everything by cos to the whatever the highest power is there. And in this case, that's 3. So divide everything by cos cubed, and we end up with a whole heap of sine on cos, sine cubed on cos cubed, sine squared on cos squared, and so on. And all of those tidy up, sine on cos being tan. And we get our relationship, 3 tan theta minus tan cubed over 1 minus 3 tan squared. Okay. I'm going to solve this equation. In fact, they've kind of helped us out. They've told us one of the solutions already. Show that. Initially you'd think, oh, I'll just substitute in. No, that's really going to help because we don't know what the exact value of cos pi on 9 is. So to sub straight in, no good. So I'm going to do it a different way. 8x cubed minus 6x minus 1 equals 0. Now, those of you observant will notice the numbers 8 and 6, which are multiples of 4 and 3. Why is that significant? Let's go back to what we just proved. There's those numbers 4, 3. So I'm going to take advantage of the relationship we just proved. Because I'm now going to say, well, okay, we're going to let x equal cos theta. And so I have 2 lots of 4 cos cubed minus 3 cos. But we just showed that was equal to cos 3 theta. And I can end up with a much easier solution, or not solution, much easier equation to go and solve. So I now can rearrange that. Cos 3 theta is a half. So, well, there's obviously an infinite number of solutions. The trick with these is you just want consecutive solutions. So the first solution would be pi on 3. Then I'd be in the, cos is positive, 4th quadrant. So that would be 5 pi on 3. Then I'm back to the first quadrant again, 7 pi on 3. And I'll stop there because I know it's a cubic I'm solving. So 3 solutions is what I'm looking for. There's no need to keep going and keep going. Well, that's 3 theta. So theta is pi on 9, 5 pi on 9, 7 pi on 9. Because it's not theta we're looking for, it's x we're looking for. And we said x was equal to the cos of theta. So x is cos pi on 9, cos 5 pi on 9. Well, I've done a bit more than what the question asked for. It only asked for cos pi on 9, and I've done that. So yeah, cos pi on 9 is indeed a solution. We're now going to evaluate cos pi on 9, cos 2 pi on 9, cos 5 pi on 9. We just said the solutions were cos pi on 9, cos 5 pi on 9, and cos 7 pi on 9. So they're the roots. We're basically looking at playing with product of the roots. Only problem is I've got a 2 pi and 9 instead of a cos 7 pi and 9. But I could rewrite. So the product of the roots we're talking about is an 8. But cos 7 pi and 9 I can rewrite as minus cos 2 pi on 9. And so then we have it. I substitute that in and we're going to get minus an 8. Because remember, 7 pi on 9 would be an obtuse angle. We're in the second quadrant. So cos is negative. And the acute angle would be 2 pi on 9. So that's how we get the 2 pi on 9 in that one. This relationship of z to the n plus 1 on z to the n and the minus 1 on 2, very handy in some questions. Now, it is okay to just quote this result. Sometimes they might ask you to prove it though, and so obviously you got to prove it. So that's what we're going to do here. We're going to find what these actually end up being. So z to the n would be cos n theta plus I sine n theta. 1 on z to the n, well I could write that as z to the negative n, so that'll become cos negative n theta, I sine negative n theta. But cos is an even function, so negative n theta, same as cos n theta. Sine is an odd function, minus I sine n theta. Or another way of thinking about that is, if the angle is minus n theta, that's a reflection of n theta in the real axis, so it must be the conjugate. So we get cos n theta minus sine n theta. Either way, that's what we get for 1 on z to the power of n. So if we add them, the sines cancel, and I get 2 lots of cos n theta. And if I subtract them, now the coses cancel, and I get 2i sine n theta. So as I say, those results you can quote and use them, unless of course they're asking you to prove them in the question itself. So how do we play around with this idea? Well, cos cubed, I can rewrite cos cubed theta now in terms of just multiples of theta, so no powers of theta. How does that come in handy? That could come in handy later, I guess, with integration of trig functions. Because when you have to integrate powers, that can, it's quite a long process. But if I've just got it as a multiple, very easy to integrate. That's a long way off yet. But all right, so what I could do is I could say, well, look, 2 cos theta I know is the same as z plus 1 on z. Now, if I raise them both to the power of 3, then on the left-hand side I get 8 cos cubed theta. And that's what we're trying to rewrite. On the right-hand side, I've got z cubed plus 3z plus 3 on z plus 1 on z cubed. Beautiful thing about binomials, when you expand them out, you get lovely symmetry with the coefficients. So you can always regroup them to get those little things with the same coefficient, and you end up with something like this. Z cubed plus 1 on z cubed, and the other one becomes 3 lots of z plus 1 on z. Well, the z cubed plus 1 on z cubed is 2 lots of cos 3 theta, and the z plus 1 on z is 2 lots of cos theta. Don't make the mistake of going 2 to the power of n. A lot of people do that. It's always 2 times. So ours changes because we had 3z, so we end up with 6 cos theta over there. Well, that's 8 cos cubed, so 1 cos cubed must be a quarter of cos 3 theta plus 3/4 of cos theta. Ooh, playtime.